Well, howdy there, Internet people. It's Professor Leach again. Today we're going to talk about finding antiderivatives. The important thing to recognize when we're finding antiderivatives is that we actually already know all of these things. We just need to modify it a little bit. And what I mean is that all the derivatives that we know are now integrals that we know. Everything we knew about derivatives has to become a thing that we know about integrals. Last week, if you would recall, we talked about writing powers of x, where we just inverted the process of taking a derivative of a power of x. The derivative says multiply by the exponent, then subtract 1 from the exponent. So the integral does the inverse operations in reverse order. Add 1 to the exponent, divide by the new exponent. Problem came up. Can't do this if n is equal to -1, so we use this whenever n is not -1. And we use the natural log to cover us in the case where n is equal to -1. We get a lot of mileage out of these two together, because writing powers of x, just like with derivatives, writing powers of x is often a good strategy. And then we did a couple of examples. I don't recall doing this example, but I usually do these 3 examples: x to the 1/2, x to the -3, and then a rational function where the denominator is one term and we can use the distributive property. So here we are using the distributive property. One term denominator. With a one-term denominator, we can use the distributive property.
Can't we technically use the distributive property if there's more than one term?
We could, but then we'd have more than one term in all of the denominators, so that might not help. That doesn't help us write powers of x. So if the denominator was x squared plus 1, I could say it's x squared over x squared plus 1, but that doesn't help us write powers of x. So use the distributive property to write powers of x. So we can use the distributive property to write powers of x. You're right, we can always use the distributive property, but if there's more than one term in the denominator, it's not necessarily as useful. And it's not useful to write powers of x, which is what we wanted here.
And how did the 1 above turn into an x? Isn't 1 just 0?
1 is 1x to the 0, so we add 1 to
Oh.
the exponent and divide by the new exponent. The derivative of 1 is 0, but the antiderivative of 1 is x. All right. We need to add to our list of derivatives or antiderivatives that we know. So let's do that. Here are the next 3 big important ones. So recall that the derivative, so we know that the derivative with respect to x of, say, e to the x is e to the x. The derivative of e to the x is e to the x. So what this means is that the antiderivative of e to the x dx is just e to the x plus c. All the derivative rules that we had before are now integrals that we have. Other important ones. We know that the derivative of sine is cosine. And so this tells us that the integral of cosine is sine plus c. Actually, I shouldn't just box this part. It's the whole thing that we want. So remember, the derivative of sine is cosine, so the antiderivative of cosine is sine. We got to remember that just because we're doing a thing with cosine does not mean the negative shows up, because we're doing a different thing. We're doing an antiderivative. So if we have the derivative of cosine x is sine x. Now we're going to do a little bit of algebraic sleight of hand because we're not going to, oh, sorry. What's missing? What did I forget?
Plus c.
Derivative of cosine is negative sine. And so the integral of sine x dx is negative cosine x plus c. So we could think, so we just have to remember that the integral of sine x is negative cosine x. The integral of cosine x is sine x. The mnemonic that I use to remember that is that the integral of sine x is negative cosine x, and the integral of cosine x is sine x. I've been told that my mnemonics aren't very mnemonic-like.
Professor?
Yes.
If I was to, like, for example, try to say those lines in like a sentence to someone, how would I say it properly? Like,
I'm sorry, I'm not sure I understand the question.
or like or no, I'll think about it and ask later. I have to rephrase my question.
Okay. So this is an important thing to notice. Notice that we have the integral of, sorry, the derivative of cosine is negative sine. And so the integral of sine is negative cosine. If we think about what happened, we know that if we take the derivative of negative cosine, we end up with positive sine. So that's a variation on this one. We know that the derivative, if we're worried about that negative thing, remember that the derivative of, let's say, negative cosine x is positive sine x. We can just take this equation and multiply everything by -1. And that multiplication goes right through the derivative because the derivative is a linear operator. So what this means is that if we integrate negative sine x, we'll end up with cosine x. Kind of match these up really weirdly. The important thing to note here is that when we take the derivative or when we take an integral, we can just multiply everything by a -1. So integral of sine x to x is negative cosine x plus c. So it's important to recognize that integration and differentiation, we can just, it goes right through any constant multiples. So we can multiply or divide. Integration and differentiation go right through constant multiples. Integration and differentiation they go right through the constant multiples. To take the derivative of x squared, it's the same process as taking the derivative of 5x squared. The derivative doesn't care about the 5, we just multiply by 5. So the reason that we want to bring this up is that we don't always want to just take the derivative of plain sine of x, cosine of x, or e to the x. There might be a constant up in there, and we have to be able to deal with that. So let's deal with that. So we know that the derivative of e to the k times x is k times e to the kx, just using the chain rule. And we want to be able to see the chain rule. When it's e to the kx, it's the chain rule when we take the derivative of sine of kx, and we get k cosine of kx, or the derivative of cosine of kx is negative k times the sine of kx. We want to see the chain rule when the derivative of the inside is just a constant. So that's what's going on in these examples. So this is the chain rule. Where the inside is linear. That is, the derivative of the inside is constant. So the chain rule is easy to apply when the derivative of the inside is just a constant. The chain rule is easy to apply where the inside is linear, because the derivative of the inside is just a constant. So the derivative of e to the 5x is 5e to the 5x. The derivative of sine of 7x is 7 cosine of 7x. The derivative of cosine of 12x is negative 12 sine of 12x. So in all those cases, we're using the chain rule because we're always using the chain rule. The derivative of the inside was just a constant, so we just multiply by that constant with derivatives. We have to translate this to antiderivatives of e to the kx. So, or when we're trying to integrate. Sentences are difficult today, apparently. So if we're going to integrate e to the constant times x, we should get the same form like we had here. We should have an e to the kx plus c. But when in the derivative, we take the derivative of the inside and we multiply it. When we're integrating, we're not going to multiply by the derivative of the inside. What's going to show up in front? Anyone want to guess? While I take a sip of coffee.
Well, if we're not multiplying, I'm assuming we're going to divide.
It's almost like it writes itself. You're absolutely correct. We're just going to divide by the constant. And remember how this works. We're trying to find an antiderivative. So if we take the derivative of our answer, we should be back to where we started. The derivative of 1 over k e to the kx is 1 over k times k e to the kx. And so the k's cancel out, and we're back to where we started. So we've expanded a little bit with the anti-chain rule. So if we want to integrate the sine of, oops, I did this in the wrong order. Integral of sine of kx dx. We're going to have a negative cosine of kx plus c, but instead of having a k like when we took the derivative, we'll have a 1 over k because we're going the other direction. The derivative of cosine of kx is sine of kx times k, and the k will cancel out the 1 over k to get us back to where we started. Similarly, the integral of cosine of kx dx is 1 over k times the sine of kx plus c. Multiply by the derivative of the inside, and when the derivative of the inside is a constant, we just get to divide. Everything is nice and straightforward because it's constant multiples. Still having trouble putting sentences together. So if we had, for example, we wanted to integrate 5 times the sine of 3x dx. The 5 is just a constant multiple, and that will get carried along. The integral of sine of 3x is minus 1/3 cosine of 3x. So the derivative part, or sorry, the antiderivative part is minus 1/3 cosine of 3x plus c. The 5 is a constant multiple, just gets carried along. Any questions?
So essentially, you're just reversing chain rule.
Yeah, it's a reverse chain rule. And
Okay.
it's an easy application of chain rule, so that's why it's easy to summarize here without going into a full anti-chain rule.
Got it.
The full anti-chain rule is integration by substitution, but we want to be able to do these just by looking at them. So
Right.
for another example, let's suppose that we wanted to integrate 7e to the negative 2x dx. The 7 is just a constant multiple. The negative 2 is going to be like the k. So the 7 just gets carried along. The antiderivative of e to the negative 2x is going to be an e to the negative 2x divided by the derivative of the inside. It's kind of an unhealthy way I said it there, divide by the derivative of the inside, but the derivative of the inside is just a constant, so that's okay.
Okay. Thank you.
So let's see. We should talk about one of our favorites. A lot of times when we're applying functions of the form e to the x, when we're looking at e to the x, we're looking at functions that are undergoing continuous change. So a lot of times we're going to have values that are less than 1. We're going to have decimals as coefficients of our x in our e to the x functions. So we'll have something like 100, let's say 200. I don't know why I felt the need to change that. E to the negative 0.4x dx. And we do the same thing that we did in the previous one. The numbers just look different. But here's like a decreasing exponential function. This is something that we see all the time. We use the exponential functions to model a lot of things. But we do the same thing. Instead of 7, we have 200. We still have an e to the negative 0.4x because the exponential part doesn't change its form. And we'll divide by a negative 0.4. Now, this is not a good number to write. You don't leave decimals in your fractions. That's just bad form. Also, the negative is in the denominator. That's also bad form. Technically not incorrect, but technically not incorrect, but I mean improper.
Would you just divide 200 by 0.4 to simplify, or this is what you want to see?
No, I want to simplify. If it's just anytime you have a bunch of constants mushed together, simplify that. So 2,000 divided by 4 is what, 500? So minus 500.
Okay.
E to the negative 0.4x plus c. So yeah, definitely simplify your constants.
Will do.
Otherwise, you're asking me to simplify 200 divided by 0.4, and then you're leaving that up to me, and I always divide it wrong when I'm correcting quizzes. I don't know what that is. I think I did it right here, but like if it was a quiz and you left it this way, I'm like, oh, 200 divided by 0.4, 20. Oh, nope, that's not correct. So don't leave it up to me.
Got it.
Any other questions? So what we have here in these three is a simplified version of the chain rule, which technically we don't see until chapter 7.1, where we're talking about integration by substitution. But this one's this one is the easiest one to implement. We get to divide by the derivative of the inside because the derivative of the inside is just a constant. That's the important thing to take away moving forward with these simple ones. We get to divide by the derivative of the inside because the derivative of the inside is a constant. We get to divide by the derivative of the inside we get to divide by the derivative of the inside as an anti-chain rule because the derivative of the inside is just a constant. That second part is very important. It's what makes the first part go. That's why we use the word because. Too often when we say things in math, we leave off the important parts. And so students be like, oh, you said we get to divide by the derivative of the inside. And I would say, I absolutely did not say that. I said we get to divide by the derivative of the inside because the derivative of the inside is constant. So if we wanted to do something like the integral of e to the minus x squared, like we had before, we don't get to divide by the derivative of the inside because the derivative of the inside is not constant. So for example, we don't get to just divide by the derivative of the inside because the derivative of the inside is not a constant. So the derivative of the inside is not constant, so we don't get to just divide. Question?
Yeah, sorry. So we can do that with, or we can divide by the derivative of the inside because the derivative of the inside is constant when it's like for the example of negative 0.4x, but not x to the second because there's no constant in front of it.
No, because the derivative of the inside is negative 2x, not just negative 0.4.
Okay, got it.
So even if it said, so it's not that there's a constant in front, it's the exponent on the x. So e to the 5x squared dx. The derivative of the inside is not a constant, so we don't just get to divide by it. So it's not the constant in front, it's that the derivative is just a constant.
Oh, I see. So because it just has x, when you take the derivative, that itself is just a constant.
In this example, the derivative of the inside is negative 2.
Right.
So here, let's see, derivative of the inside is negative 2, which is a constant. The negative 0.4, the derivative of the inside is negative 0.4, just a constant. The derivative of the inside here is negative 2x, not constant.
Got it. I understand. Thank you.
Any questions? This is our introduction to the anti-chain rule by looking at this simple case that we're going to want to apply without having to do the anti-chain rule notation all the time. Any questions?
What would the derivative or the antiderivative of e to the negative x squared be then?
We don't have one. So e to the negative x squared is a strange function. It does not have a nice antiderivative. I would have to construct an antiderivative using the second fundamental theorem of calculus. So this is not the derivative of any nice function. And by that, I mean finite combination of elementary functions.
Is that something we'll be learning this semester?
Yes. Yeah, when we talked about, last week, we talked about the fundamental theorem of calculus and how we could always construct an antiderivative with a definite integral. Moving forward, one of the things that we have to figure out, one of the skills built into finding antiderivatives is recognizing what technique will work for a particular function. Just like with derivative rules, you have to learn when to use the product rule and when to use the quotient rule and when to use the chain rule. So you have to learn how to decide which rule to use and then use the rule. The same thing happens when we're doing integrals. We have to learn which rule to use and then how to use that rule. So part of the problem is deciding what rules are in play. Any other questions? All right, so this week, no, it's not that negative x squared is not constant. The derivative of that, negative 2x, is not constant. The derivative of the inside is not constant. The reason that I use the phrasing derivative of the inside is that it's a very common phrasing to show up in a chain rule when we're describing the chain rule with words. It's a little bit hand wavy, so it's not my favorite, but it is the most common that I encounter. So that's the one that I use. All right. Okay, so this week you're working on quiz 3 and quiz 4 is probably going to show up. If you didn't see a quiz 4 come in this week, then you need to see patterns more. You should expect more things. Because we did this completely new thing. It's just going to be finding a bunch of antiderivatives and practicing typing those antiderivatives into text boxes on Canvas. Because we got to learn how to type math. So you're working on quiz 3, the quiz 4 that hasn't shown up, and you've also started working on the chapter 6 homework, which is technically due on Monday. So if you don't start the homework until Sunday, that's a bad way to go about things. If you don't start the homework before we start discussing it in class, that's also a bad way to go about things. You don't want to walk in and say, hey, I'm going to be covering chapter 6.3. And you're like, oh, good, I haven't started that yet. Now I won't have to do it at all. All right. That's going to do it for today. No, e to the 5x squared is not constant. It's got the variable x in it. So that's not what I was asking. That's not what we're concerned about with either. We're trying to decide when I can just divide by the 1 over k. When do I get away with 1 over k e to the kx? And that only works when we have 1 over some constant, when the derivative of the inside is a constant. This is not constant because it's got an x in it. So it's a variable expression. All right, well, that's it for today. Anyway, it's just a thought. Y'all have a good day.
Thanks, brother.